Welcome. In this second video, we're going to look at some vector operations and components and some applications. So if we have two vectors, we've got highlighted v and u up above, v with components v sub 1 and v sub 2, and the vector u with x and y components we're listing as u1 plus u2, then what we're indicating here is that we can do vector operations component-wise, all right, meaning we would just simply add the x components and add the y components together to write the sum vector down. So that makes it very nice to do that. To do subtraction, you just subtract component-wise. Subtract your x component, subtract your y components. Now, to do scalar multiplication, I'm going to just kind of illustrate that, and then we'll look at the result listed. If you want to multiply a vector by a scalar, well, you're going to scale that vector, so we want to evenly scale both the x and the y component. What we do is just distribute that and multiply both the x and the y component by that constant. All right, so let's get some examples taken care of there. If I want to write the vectors u plus, I'm just going to do, for some of these, I'm not going to do each part for example 5. So let's do for part A, u plus v, and then u minus v. So writing the vectors down, we're just going to add your first components together. 2 plus 1 is 3, and then negative 3 plus 1, or negative 3 plus 5, pardon me, is 2. So the vector sum is 3, 2. For the vector difference, we're going to have 2 minus 1 is a difference in your x components. Negative 3 minus 5, that's going to be negative 8. So be careful with the minus signs. All right, so there we get u plus v, u minus v. For part B, let's just do the third part listed, which is this, what we refer to as a linear combination, 2u minus 3v. All right, so the first thing we need to do is do the scalar multiplication. So we're going to multiply the 2 through the first vector, multiply the 3 through the second vector, and then subtract. So writing that out, we would get 4 comma negative 6, and then we're going to have minus, distributing the 3 through, it's going to be 3 comma 15. All right, next we are just going to subtract component-wise. All right, so after we did the scalar multiplication, 4 minus 3 is 1, negative 6 minus 15, we're getting negative 21. There we go, that's it. All right, so vectors given in components are very nice to work with in terms of some of these basic operations of addition, subtraction, scalar multiplication, or combinations of those operations. Okay, there's some other notation we might encounter, in working with vectors, and that's the I-J notation. We refer to I and J as the standard basis vectors. They are the vectors 0, 1 and 0, negative 1. All right, it turns out you can write any vector as a linear combination of I and J. So for instance, 3, negative 4, that vector we can write in terms of I and J as 3i minus 4j. So 3 is the x component, minus 4 is the y component, and those are the coefficients of I and j respectively. All I've done below here is just list out why we can do that kind of in reverse. So in the first step here, we're just rewriting that 3, negative 4 as a sum of those two vectors, 3, 0 and 0, 4. And then we're actually factoring out the the 3 and the negative 4 here to outside of these vectors. And then that's just 3 times the vector I plus or minus 4 times the vector j. You might see, and I have a tendency when I'm writing this on paper to put little hats on top of the I and the j, kind of indicated here. That's just done sometimes in some references, so just be aware of that. If you see the little hat, that's just the way some folks write vectors out. All right. Do a little bit of practice with the vector, the I-J notation. So again, I plus j, what would that really be? That's just the vector 1, 1, all right, in component form. So if we drew that out, I have that listed in green here. And if we took the magnitude, it'd be the square root of 1 squared is 1, plus 1 squared is 1, which would give us the square root of 2. The vector v2 is 3, negative. The negative 3, 5, I drew that in blue on the screen. So again, we're going from the origin, basing at the origin, 3 to the left, up 5, put that point down, and then draw the directed arrow. Computing its magnitude, we get the square root of 9 plus 25, which is the square root of 34. We can't simplify either of those magnitudes down. That's it. Okay. All right. Now, what we're going to do next is write out a formula for determining the components of a vector in terms of its magnitude and its direction. All right, so what we're thinking about doing is if we have a two-dimensional vector plotted like I have on the left side here, v, and again, I'm going to use r just for simplicity of writing some things down, but r in the picture is the same as the magnitude of the vector v. Okay, so r and magnitude v are one and the same for this discussion. All right, what we think about doing is if we have a vector plotted in standard position, the angle theta is always the angle from the positive x-axis to your vector. Okay, now if that vector is in quadrant 2 or 3 or 4, it's still from the positive x-axis over to your vector. Okay, all right, so let's make sure we keep that in mind when we're doing calculations. And we can just read some things off of this picture. So I'm just going to highlight it and then I'll take it off. From the vector tip, we could drop down a perpendicular, and that creates a nice right triangle for us. Okay, so when we draw a vector normally, we're not going to have that right triangle in that. We're just doing this for derivation purposes. Now, if we look at our picture, we've got a nice right angle triangle. The adjacent side is x, the opposite side is y, the hypotenuse is r. So if we just read off from our picture, we've got cosine of theta is x over r, sine of theta is y over r. If we isolate x, we could do that by multiplying both sides by r there. Okay, and a similar thing for solving for y. If I multiply both sides by r to clear the fractions out, we get this nice statement that x is r times cosine of the angle theta. Y is r times sine of the angle theta. But again, r is just the magnitude of the vector v. So when we write this out, this shows we can write the x component as the magnitude of the vector, the length of the vector, times cosine of the angle it makes with the positive x-axis is the x component. The y component is the length of the vector times sine of the angle theta, where that angle theta is the angle from the positive x-axis to your vector. So that's very nice. If we know the magnitude and the direction, we know the angle, or we can figure the angle out, then we can write the x and y components down and then work with whatever we need to work with. What we also have is another pair of useful feature of things that I have in green on the right side of the screen, that the magnitude, we already knew that formula is the square root of x squared plus y squared. So if we know the rectangular coordinates, we can figure the magnitude out. If we know the rectangular coordinates y and x, we can also use that triangle, because tangent of the angle theta will equal opposite over adjacent, and that will be y over x. That will allow us to determine the angle theta. Right? We might have to make some adjustment depending on what quadrant we're in, but that equation, tangent of theta equals that ratio, y over x, will help us determine theta. All right, let's get a couple examples worked out here. So example 7, it says, from the given magnitude and direction, write the vector in component form. So for part A, do that here. All right, so for part A, we've got magnitude 6. All right, and the direction is 45 degrees. So we're just plugging it into the formula up above here, which I'm just going to circle. Then I'm going to take that off. Okay, so again, magnitude is 6, and the angle is 45 degrees. So we're just putting in 6 for magnitude, and then cosine of 45, and then 6 for the magnitude, sine of 45. Now, we can do a little better than that. Cosine of 45 degrees is a known trig value to us. It's the square root of 2 over 2. We can write that down on paper. So we're going to put that in now. And sine of 45 degrees is also the square root of 2 over 2. And then we can simplify that just briefly here, right? 2 goes into 6 3 times. So we could rewrite this vector more simply as 3 times the square root of 2, and then 3 times the square root of 2 in the x and the y components. If we wanted decimal versions, we could then convert that to a decimal form by plugging it into a calculator. For part B, for the vector, we'll call that vector W. All right, the magnitude is 8. The direction, when we say direction, we're assuming that's implying it's the angle from the positive x-axis as we have drawn there on the left side of the screen. So we're having 8 times cosine of 220 and then 8 times sine of 220. Our reference angle here, which is always between the x-axis and the terminal side of your vector or your angle, is 60 degrees, right? So 220 minus 180 is not 60 degrees, sorry, that would be 240. It's 40 degrees. That's my mistake there. It's 40 degrees. So for this one, we don't know that value, so we're going to have to compute, or we don't know that angle, right, the reference angle. Just realizing that I made a mistake there. That angle right there is 40 degrees. Okay, so we would have to plug this into a calculator. So if we just do this calculation, so get a calculator and compute, and just plug in the angle, 220 to the cosine, multiply it by 8, plug in 220 to sine, multiply it by 8. If we do that, we're going to get these approximate decimal values. So we're not going to be able to get an exact value down, but we're going to get approximately equal to negative 6.128. I'll just go to 3 decimal places, and negative 5.142. All right, we go to 3 decimal places. So that one we can compute to get our decimal values for that second angle. All right, the last thing we're going to talk about is resultant forces. All right, this is an application with vectors. If two forces act on the same object, the net effect on the object is referred to as the net force or the resultant force, and it's really just the sum of the two vectors. All right, if you have more than two forces acting on the same point, then the resultant would be the sum of however many you have, 3, 4, 5, whatever you have. Okay, so let's do one last example, which says 3 forces act on an object. We've got them listed in component form here, F1, F2, and F3. We want to find the magnitude and the direction of the resultant force. So I'm going to call the vector capital F the resultant, right? And notice the resultant here is F1 plus F2 plus F3. So we just write our vectors out, add the x components. So we have 8, negative 8, plus 0, plus 4. That comes out to negative 4. Got that written on the next page here. And then the y components, negative 5 plus 1, which is negative 4, minus 7 is negative 11. So we get negative 4, negative 11. So we have the resultant force given to us in component form. Now we need to convert that over to find the magnitude and find the direction. So we're going to plug in negative 4 and negative 11, which is going to give us 16 plus 121. All right, so we get the square root of 137. All right, so we can compute that as a decimal if we want, or just leave it in terms of that square root, which I'll do for the video. All right, so there's the magnitude. That's the easier part. Then the direction is a little bit tougher to determine. So let's take a little time with that. All right, so let's draw a picture. I've got that listed down below here. Okay, so we've got the vector here drawn, and I'm just going to add a little to the picture. All right, so again, the vector itself was the vector negative 4, negative 11. That's our vector capital F. All right, and again, we know, and we could add a right triangle to this, but we said before that tangent of theta is y over x. So our y value is negative 11. Our x value is negative 4. All right, and the negatives cancel. This is the same as 11 over 4. All right, now, how would we solve that equation? What angle has a tangent value of 11/4? That's not a common output value for tangent, but we know one solution can be found with the inverse tangent function. So it would be arctangent or inverse tangent of 11 over 4. All right, so now if we plug that into a calculator in degree mode, you're going to find out that that comes out to 70.01689. I'm going to go to this many decimal places. That's in degrees. Now, that's not correct. Okay. So what I have listed here is, and shown in the picture in green here, we got 70.01689. That's an angle in quadrant 1. We need the angle theta to go from the positive x-axis over to our vector, which is in quadrant 3. Well, we can see what we need to do. We need to add on, to get our angle theta, we're going to need to add on 180 degrees. That makes sense from our previous experience. Tangent is a pi periodic function. So for us, we need to add on 180 degrees to get another angle whose tangent will be 11 over 4. And that comes out to 250.01689 degrees. So that sometimes happens. If we are working with inverse tangent in our vector is in quadrant 3, then we are always going to have to take what our calculator tells us and add 180 degrees to that, or add pi radians to obtain the appropriate angle. And that's it for this recording.